the least squares line and the correlation coefficient. Let's consider a scatter plot that we've seen before with motorboat registrations in thousands in Tallahassee, Florida on the x-axis and manatee deaths on the y-axis. There are many lines that appear to fit the data well. This one, this one, this one, this one. There is one line that is often said to fit the best, especially when there are no outliers, and it's called the least squares line. So let's pick arbitrarily one actual point and directly below it the predicted point, predicted by the model. As we learned before, that is the error or residual. So if we draw a square and look at its area, the area of that square is equal to error squared. Every point has an associated square which is represents the error squared for that particular data point. The least squares line is the line that, and this is a very important phrase, minimizes the sum of the squares of the errors. It's the line for which the sum of the errors of all of these individual squares is the smallest. So that's, in short, what the least squares line is about. We have qualitative ways of expressing how appropriate the linear model is, like a very appropriate model, a fairly appropriate model, or an inappropriate model. There is also a quantitative way to express the goodness of fit, and it's called the correlation coefficient. The correlation coefficient, R, measures the strength of the linear relationship. And the word linear is very important. The linear relationship between the two variables. The range of R is -1 to 1 inclusive. -1 means a perfect linear correlation. The line has a negative slope. 0 is no linear correlation. And 1 is a perfect positive linear correlation, which means the line has a positive slope. And here are 4 regions that go from -1 to 1 and what those regions correspond to. So a correlation coefficient of 1 means that all the data points are directly on the line. In this case, all of the data points are hidden because they're below the line. Now as we go to r is equal to 0.9, you can see that data points have moved a little bit from the line. 0.8, 0.7. You can see already at 0.7 it's starting to be that the residuals are starting to be fairly big. 6, 0.6, 0.5, 0.4. And at 0, there is no linear correlation. There's no evidence that there would be a positive slope or a negative slope, for instance. And so here we go into negative correlation coefficients until we get -0.7, -0.8, -0.9, and then -1, a perfect negative linear correlation. So here's going back to the picture where r is equal to 0.8. Are all scatter plots for one r value the same? Definitely not. Here are a series of situations of scatter plots where the correlation coefficient is 0.84 in every case. One of the things that we can see here is that it looks like maybe there's going to be some sort of exponential relationship. Anyway, this only tells us the strength of the linear correlation. It's not telling us about any other models. So all of these are cases in which the correlation coefficient is 0.84. There are an infinite number of scatter plots that have any given R value. And that's a brief introduction to the least squares line and the correlation coefficient.